Have you ever considered how a push or a pull, an everyday interaction, can become a cornerstone of complex scientific understanding? Imagine trying to describe such an action without mentioning where it is going. Electric force is fundamentally a vector quantity. This means it has both a specific magnitude, which tells us how strong the force is, and a precise direction, indicating the way it acts upon a charged object. Understanding these twin properties is essential for accurate analysis in electromagnetics. The vector nature of electric force arises directly from the interaction between charged particles. According to Coulomb's law, the magnitude of the force between two-point charges is proportional to the product of their charges and inversely proportional to the square of the distance between them. The direction of this force, however, is determined by the types of charges involved. Like charges, such as two positive charges or two negative charges, exert a repulsive force on each other, pushing them apart along the line connecting their centers. Conversely, opposite charges, like a positive and a negative charge, exert an attractive force, pulling them together along that same line. When multiple charges are present, the net electric force on any single charge is the vector sum of all individual forces exerted by every other charge, a principle known as superposition. To accurately calculate and representing electric forces, you will typically follow a few key steps. First, it is crucial to draw a free body diagram for the charge you are analyzing, showing all other charges interacting with it. Next, identify the direction of each individual force, remembering that like charges repel and opposite charges attract. Third, calculate the magnitude of each individual force using Coulomb's law. Finally, and this is where the vector aspect truly shines, resolve each force into its component vectors, usually along the x and y axes. Then, sum these components separately to find the total x and y components of the net force. From these net components, you can then determine the overall magnitude and direction of the resultant electric force. This vector approach is not just a mathematical exercise. It is the backbone for understanding electric fields themselves, which are also vector fields. When you encounter a concept like a force field, it is inherently describing how a force would act at various points in space, including both its strength and its exact trajectory. This meticulous attention to both magnitude and direction allows engineers to precisely predict how charged particles will behave, which is critical in designing everything from microprocessors to high-voltage transmission lines. For instance, correctly modeling the vector forces in an electron beam is vital for display technologies and particle accelerators. Grasping that electric force is a vector, with both magnitude and direction, provides you with the foundational toolkit to interpret and analyze complex electrostatic systems. By diligently applying vector addition and understanding the directional interplay of charges, you unlock the ability to accurately predict interactions and movements of charged particles, paving the way for deeper insights into electromagnetic phenomena and practical engineering applications.